tomorrow afternoon, there will be bus perturbation again, starting at 2 p.m. So the whole afternoon. You can check the Mathématiques webpage for more details. And second announcement, would anyone be interested to borrow a laptop for this afternoon exercise session with Walnut? Anyone? Okay, okay, no one else. So now we are happy to have again Sylvain Perifel to continue his lecture.
Thank you. So good morning, everyone. So today I'll speak about randomness and algorithms. Okay, so and the talk will be divided in two parts. The first one will be about algorithms using randomness. And the second one will be about randomness itself, what is a random sequence, and so on. Okay. So let me start with a specific problem, which is called PIT. And as everyone knows, PIT stands for polynomial identity testing. Okay. And the goal of this problem, so this is you have a given polynomial in a compact form, which is given by a circuit, actually, an arithmetic circuit. I will explain that later. And the goal is to decide whether this polynomial is zero, so identically zero. Okay? So the input is a circuit, so an arithmetic circuit, computing a polynomial p of x1, xn, xk, let's say. And the question is whether this polynomial is zero. And let's say we are working over the fields of the real numbers, but it doesn't matter much. Okay, and before I explain what an arithmetic circuit is, let me simplify this problem for you. No, actually, this is equivalent, so this is not a simplification, but we will not talk about polynomial here, but only about integers. Okay, so let me call it IIT, integer identity testing. And instead of computing a polynomial p, we just compute an integer n. And the question is whether n is zero. Okay? So now we are just over the relative numbers, okay, over z. And we have this question. So why do I take the liberty to replace polynomials by integers? Actually, because the problem IIT is equivalent to PIT for the notion of equivalence we've seen on Monday. Namely, PIT reduces to IIT. So this is the same complexity. So that's why I will talk about integers, because it's easier to explain. Okay. All right, so I need to explain now what is this thing. And as you will see, this is just actually a sequence of addition and subtraction and multiplication that compute an integer. So let me draw a picture. I will draw it here instead. Let me make a picture. You have as input the constant, let's say, okay, to simplify things, I will just take the constant -1. This is the only constant that you have. And you will be able to make multiplication and additions from this constant. So for instance, you can just here multiply -1 by itself. So you obtain the value 1, of course. And then you can, for instance, add 1 with itself to obtain 2. And for instance, you can do it again. Here, you multiply, you obtain 4, or you could just sum. And then you can do this if you want. And here you obtain a circuit that computes the integer 3. Is that clear for everyone? Yeah, okay. So you start from -1 and you have a series of multiplication and additions and you obtain an integer. Very easy. And you probably wonder why I'm speaking of such a trivial problem, because you just have to compute the integer and test whether it is 0. Okay? So let's do let's write this algorithm. So this is a deterministic algorithm. Deterministic meaning normal, okay? So not like NP last time. Deterministic algorithm. So compute the value, okay, iteratively, let's say, iteratively, the value of each gate, starting from the input gate, which is a constant, and then accept, if and only if, the value of the output gate is 0. Very easy. So, what is the complexity of this algorithm? It seems that the complexity is roughly the number of gates in the circuit, but actually it is not. Actually it is not, because does anyone see why it's more complicated than this? Yes, exactly. The numbers can be huge, actually. So let's figure out this example. You start from -1. Okay, you start the same way here. And then you add. So here you have the value 2, the same as before. And now you keep squaring it. So you keep taking the square of 2. Again, so here you have 4, here you have 16, and so on. And you do it n times. So here, you do it n times. The value here is 2 to the 2, here is 2 to the 4, so 2 to, okay, like this, and so on. And the value here is 2 to the 2 to the n. So with n iterations, you've computed 2 to the 2 to the 2 to the n. Okay. So this is an integer which takes an exponential number of bits to write. Okay. So actually here, the value of each gate, the value can have an exponential number of bits. So this very simple algorithm actually is exponential. Okay, so this is an exponential algorithm. Is it clear for everyone, or? Yeah, just because when you want to write the numbers that are computed there in the circuit, the number of bits is exponential, so you have to take an exponential time to write the number. All right, so you can wonder whether we can do better. Actually, not much if we stick to deterministic algorithms here. If we want something deterministic, it's not clear how to do much better than this. And this is roughly the best algorithms we know. Okay. However, we could do something different to avoid this, let's say, overflow of, this expansion of bits. We could compute modulo something, modulo a small number. Okay. Okay, but which small number can we take? Actually, we can take it at random. And this something that we will, this will give actually a randomized algorithm that I will explain now, which is much more efficient. Okay, so because here, this exponential algorithm places the problem IIT or PIT anyway, this is the same, in the class exp of exponential deterministic time that we have seen last time. Okay, and what I will explain now is how to improve this and put it in a much smaller class, possibly much smaller class, which is randomized. So let me explain this now. Okay. All right. So now we will just avoid the growing size of the numbers that are computed by taking a random modulo and to compute each gate modulo this random number. So now we have a randomized algorithm, which is the following. So what we do is we repeat several times a procedure, and the number of times we will repeat it, we will try to understand what it must be afterwards. So repeat, let's say k times. So k will be determined later to be determined. So why is it important? Because this will determine the complexity of the whole algorithm. So repeat k times. Choose a random number m for modulo in, let's say, 2 and 2 to the n squared, it will be enough. So n squared, n here is the size of the circuit, the number of gates in the circuit. Okay? So size of the circuit C. Well, and compute iteratively the value of each gate modulo m. Right. So now we avoid, of course, the problem of the growing number, the growing size of the numbers, because they are all bounded by 2 to the n squared, meaning that they at most have n squared bits. Okay? So this time, indeed, this procedure is polynomial. This is polynomial, okay? And actually this is polynomial. This is not exponential anymore. So far so good. Now we have also to understand what is k, but first we'll try to understand why this is enough. So is it clear, this algorithm, for the moment? Yeah. So now let's try to see if we rather often have the good answer. So, okay, so analysis of the algorithm. So first, the number that is computed here by a circuit of size n is at most 2 to the n in absolute value. This is the maximum value that we can obtain. I mean, this is the worst, or whatever, the best strategy to compute a big number. This is the repeated squaring here. Okay. So first, remark that n is at most, in absolute value, is at most 2 to the n. Okay. We cannot do better than this using a circuit of size n. Okay, so it has at most 2 to the n different, or not different, 2 to the n prime factors. So why? Because every prime factor is at least 2, so you have at most 2 to the n prime factors. Okay? And now, for these, and now we have to understand what is the possible error that we make with this iteration here. Okay, so what can be the error here? You could possibly take a random number m, which divides the value capital N, okay? You could possibly take m that divides the final result here, but the final result is not 0. This is the only possibility that you can make an error. If capital N is 0, then of course here you will answer the number is 0, because every time you will obtain 0 here. But if the number n is not 0, possibly you could choose a random number that divides capital N. Okay? In that case, you make an error, because you will say the value of capital N is 0, but actually it is not. All right? So do you see this? Or, okay, the only possible error is when capital N is different from 0, but m divides capital N. In that case, we say, okay, capital N is 0 by this algorithm. When we compute it modulo m, it makes 0. But actually it is not, so this is a wrong answer. Okay. So we have to understand what is the probability of this error here. Okay, so let's do it. And we will make a gross estimation, which probably could be refined a lot, but this is not our problem here. It will be enough for this talk. Okay. Okay. So, what is the probability that if n is different from 0, what is the probability of picking a divisor? So this is what we have to compute. We'll try to see the probability of success, actually. We'll try to do it. The probability of success does not divide capital N. So what is the probability that m does not divide capital M? So this time, this is at least yes, this time it's correct. Probability that m does not, m is prime, and m does not divide capital N. So this time I think it's correct, I hope. Okay, yes, I think so. And so this is probability that m is prime times the probability that m does not divide n, knowing that m is prime. Is that better this time? Yeah, I think that's the way I wanted to do it before. Sorry. Okay, and now, so let's try to evaluate this. So the probability of that m is prime by the prime number theorem is at least, so how many primes are there in the interval? There are log 2 to the n squared time divided by log of 2 to the n squared. Okay, so there is a constant, let's say alpha, times 2 to the n squared divided by n squared, something like this. Okay, so this is a probability that m is prime. This is a number of prime numbers here. This is the number of prime numbers in the interval 2 to the n squared. So this is the prime number theorem here. Okay. Right, and this is the total number of elements of the interval times the probability that when m is prime, m does not divide capital N. Okay, and now this probability can be bound using this property here. Okay. So what is this probability now? It is just that you pick here you are sure that m is prime, and you want to avoid the prime divisors. Okay, so it is 1 minus the number of prime divisors is at most 2 to the n, and you want to divide by the total number of prime numbers in the interval, which is this alpha times 2 to the n squared divided by n squared. All right? Is that better now? Sorry about that. Okay, and now if we do the math, here you have 1 over n squared. This can be just, this cancels out. You have alpha time divided by n squared, multiplied by something which is almost 1. Okay? So let's say this is at least alpha divided by 2 times 1 over n squared. So this is a constant divided by n squared. Okay. All right, so we have that the probability of success is at least n squared, let's say. 1 divided by n squared. Okay? So do I need to recap something because of my mistake before? Maybe I just recap a little bit the algorithm. So the algorithm is very simple. You choose a random number m in this interval, and you compute the value of each gate modulo m. Okay? So you don't have the problem of the growing number of bits of the input of the gates, but you can make an error. And when do you make an error? The only possible way to make an error is to choose a divisor of n, whereas n is not 0. Okay? So this is the only possible way to make an error. And so we will compute the probability of error. Actually, so the only case when it happens is when n is different from 0. So let's suppose n is different from 0. And the probability of success of this algorithm is what? Is when you choose a modulo m that does not divide n. If you choose a modulo m that does not divide capital N, it means that you say, the algorithm says that n is not 0. So you're right, okay? And we do the math, and we obtain that actually the probability of success is at least 1 over n squared. All right? So we forget everything I've told now. We start from 0 again, okay? And we have the probability of success now of this algorithm, okay? This is not a lot. Suppose that the circuit, n is the size of the circuit, the gates of the circuit. Suppose you have circuits of size 100. The probability of success is 1 divided by 10,000. This is not a lot. Okay. What can we do to improve this probability of success? Of course, we will repeat this process. And that's why I said we will repeat k times this algorithm there. Okay? And what happens if we repeat k times the algorithm, this part of the algorithm? So when we have k repetition, we just need one success to be sure that n is different from 0, okay? So the probability of error is when every time we make an error, okay? The probability of error is, so we need to make an error the first time, so we need to say that n is 0 whereas it is not the first time. We need to say that it is 0 the second time also, and so on, k times. Okay. So this happens with probability 1 minus alpha divided 2n squared here. So this is the probability of error to the k. Do you see this? Yeah. So if we repeat k times, we have this probability of error. Okay. All right. And when we choose k of the order of n squared, we can make it a constant which is close to 1. Okay. If k is, let's say, I don't know how much I should take, but okay. Let's say, okay. Of order n squared, then probability of error is smaller than let's say 0.01%. Okay. Okay, we just have to repeat n squared times this step here. All right, so we have now an efficient, okay, and then we are happy with such a probability of error. Okay. Okay, so despite my mistake, I hope this is rather, I hope this is clear. Okay. And this introduces actually the randomized algorithms. What you see here is that you have a very small, you are working in polynomial time. Because, why in polynomial time? Because we need to repeat n squared times this procedure which works in polynomial time. So this remains polynomial. Okay. So you have a procedure that runs in polynomial time with a probability of error less than 0.01%, for instance. Okay. So this is what we want for a randomized algorithm. And I can try to generalize this and make some classes of randomized, languages that have randomized algorithms. Okay. So, questions so far? Is it okay? Okay. So let me recap what we've done here. We've got an algorithm that says that, look, if n is 0, then the answer, then it accepts, always accepts. Okay, there is no mistake in that case. Okay, the algorithm always accepts when n is 0, because modulo m, it remains 0. Okay. If n is different from 0, then it accepts with probability at least, let's say, 99%. Sorry, it rejects with probability at least 99%. Okay? So this is the behavior of this algorithm here. And actually, this can be generalized to a class of problems that is called co-RP. So this is a set of languages such that there is a language, A. There is another language B in P. So this is actually a deterministic polynomial time algorithm. And a polynomial P of n such that, so if for x, if x is in the language, then here you see if x is in the language, we do no mistake. So here we will have for all r in 0, 1, the p of polynomial size, x r is in B, okay? And if x is not in A, then the probability, I will explain that later, but the probability that x are in B is at most. And usually we take the value 1/3 for some historical reason, okay? So what does it mean? It means that you have a deterministic polynomial time algorithm B such that when you are in the language, for all choice of the random bits, you will be, your algorithm will accept. Okay, so there is no mistake here. For all choice of the random variables, so here for all choice of m, you will accept. On the other hand, if you are not in the language, so if n is different from 0, with high probability, with small probability, let's say, on R of size of this size, so the probability is on the word R of polynomial size, you will accept with small probability. All right? So this is the case when n is different from 0, and we have to reject with high probability. Okay? So this is the class co-RP. All right. So you may wonder why we have this difference between acceptance and reject, acceptation and reject. Acceptation is done without error, and rejection is done with a probability of error. Actually, there is another class which is called BPP, and which is symmetric. Let me just write it, okay? But I won't explain this further, but BPP is more symmetric, meaning that here we have, instead of this, we have the probability over R that XR is in B is at least 2/3. So this is the class BPP, where you have an error of less than 1/3 in that case, and also a possible error, but of probability less than 1/3 in that case. So this is a symmetric version of co-RP. Okay. So co-RP is, so RP stands for randomized polynomial time. Okay, RP stands for randomized polynomial time, whereas BPP stands for bounded error probabilistic polynomial time. I don't know why there is such a difference in the notations, but anyway. And the co here means that actually we are just shifting the two conditions here for RP, for the class RP, which is also a class. We just shift the probability of error here and the acceptance here. Anyway, it doesn't matter. Okay. And so why did I speak first of co-RP and not BPP? BPP seems to be a more natural class, but actually we don't know of problems that are in BPP without being already in either co-RP or RP. Actually, we know some, but they are not very natural. So we don't know, we are not aware of very natural problems which will be here, but not already in co-RP or in RP. So that's why I wanted to emphasize this class co-RP instead, because there is this natural problem that is actually very important, very central in algorithmic complexity, as I will try to explain now. Okay, is it clear for the classes here of probabilistic polynomial time algorithms? Yeah. So let me emphasize where is the randomization? It is here. You choose a random, you choose a random word of polynomial size, and you give it to your algorithm. So you have an algorithm which now is randomized. Okay, so this is exactly the M that we've chosen here. Okay, so as before, the choice of the 1/3 here is arbitrary because we can repeat the algorithm and reduce the error. Okay, so let's just mention that. All right. Okay, remark. The choice of the error 1/3 is arbitrary. so in CoRP, you could choose any constants between 0 and 1, strictly between 0 and 1. And in BPP, you could choose any constant strictly between 0 and 1/2, okay? And why? Because we can repeat, we can reduce the error by repetition. So let me try to write what it means. Proposition, let's say proposition. If you have a language A in CoRP, or in BPP also, I will try to explain why it works also for BPP, then there is, let's say, another language C in, well, B prime, let's say B prime in P, and P prime of a polynomial, such that actually if X is in the language, then of course you make no mistake as before. So for all R in for all choice of the random bits P prime of X, you will be in the language B prime, so you will accept for all choice of the random bits, as before, of course. And if X is not in A, then the probability of acceptation will be very large. So the probability of error will be very small. So the probability you still take a random bits, random bits in this set, so polynomial number of random bits, and the probability that XR is in B prime, so it accepts by mistake, okay? It accepts by mistake, is less than 2 to the minus n. So very small probability of error, which is not constant anymore, but which is very small, okay? So how do you do that? You just have to repeat a linear time your algorithm, and if you, okay, let me write it formally. So what happens, okay, so the algorithm, what is the new algorithm, let's say? So you repeat, so a linear amount, linear number of times the old algorithm, okay? And if the algorithm always accepts, then you accept, okay? Otherwise, okay, let's say you reject if and only if at least one execution rejected. Okay? So if at least one execution rejected, you are sure that you are not in the language. Okay? But if all the executions rejected, accepted, you are most probably in the language, maybe you are doing a mistake, but the mistake is very small. So probability of error is when X is not in the language, but all the execution accept. So all the executions accept. Okay, what is the probability that it happens? Well, you have this number of here, let's say k. Okay, what is the probability that it happens? The probability is at most. So the probability of error for one execution to the k, because they are all independent. Okay, so this is at most 1/3 to the k. Okay? And of course, if you choose k to be linear, here, you can have 2 to the minus n. Is that clear? So okay, you can reduce a lot the probability of error so that the 1/3 of error actually is not important. You could have much less, 2 to the minus n. Okay. So actually you can do the same for BPP. Just let me mention it. For BPP, so for BPP, you will not do this. For BPP, you will take the majority. Take the majority answer. So if most of the execution rejected, you reject. If most of the execution accepted, you accept. And so the analysis is more involved, but you can do the same using, for instance, Chernoff bounds in probability, and you can have the same result. You can just repeat a linear number of times and reduce the error by this amount. All right. Questions? No, okay. Okay. Good. So now I just want to explain what is the link of this with Boolean circuits. So this will be just an overview of what are the links between the two. And then we'll turn to Kolmogorov complexity quickly. So, I just erased something that I wanted to keep, sorry. So, I just write it again. So, for A in, let's say, core P, there is a randomized algorithm with error strictly less than 2 to the minus n. So in the previous statement, it was not strict, but now I need strict, but it's the same proof. Okay. Now, yeah, sorry.
Here, n is not related to the size of the input?
It is the size of the input here.
It is?
Yeah. It is the size of the input here. Size of x.
We don't get this from the number of repetitions we do?
So here we repeat n times, where n is the size of an input. So it means that, okay, I forgot to mention it, we multiply the complexity of the algorithm by n, but this still remains polynomial. That's why we love so much polynomials in the complexity bounds. That's because if you multiply by n, or if you compose, or whatever, it remains polynomial. So that's why we do that, okay? Does it answer the question?
Yes.
Yeah, okay.
What is the purpose to get a smaller probability of error when the size of the input is larger?
Yeah, very good question. So maybe what I will explain now will answer. So let me try. Let me try. But we are usually concerned in the behavior, the asymptotic behavior of our algorithms. So it means that the asymptotic behavior is very good here, which is satisfactory, let's say. But there is no more, there is no better justification apart from what I will just explain right now. Okay, so thank you, good question. So let's try to understand what happens now. Actually, the proposition is the following. The proposition is, thanks to that, you can see you reduce sufficiently your error, and actually you have a single random word, random choice R, which works for all inputs of size n. Okay, so for all input size n, there is a single Rn, okay? So in 0, 1 to the p of n, let's say. So this is a choice of the random bits that works for all x of size n. That works, okay. For all x of size n. So what do I mean by that? I mean that for all x of size n, so for all x of size n, we have, okay, so we have x is in A, if and only if, actually, x Rn is in the language B that was used to define A. So this is B here, is the language, okay, that defines A. This is the deterministic algorithm in polynomial time algorithm, okay? So it means that here, the choice of Rn works for every input x of size n, okay? So do you see how we can obtain such a result, maybe? Actually, we have reduced the error so much here that the probability that there is such a word Rn is greater than 0. So let's do the proof to see what happens. The probability, so this time I will think a little bit before I write the probability. So what we want to say is that, yeah, okay. Yeah. Okay, the probability that there is, no. Okay, yes. The probability that for all R, so we choose the R and the R here, for all R, there is, no, okay. The probability over R, that's what I want to say. The probability over R, that there is an input X such that we have an error. So for instance, X is in A, but XR not in B, or the opposite, or X not in A, but XR in B. Okay, so the probability that over R that there is an X which makes a mistake, for which R makes a mistake, this is less than, okay, less or equal than the union bound. I mean, you use a union bound. So this is less than here 2 to the n. So this is the number of x here times the probability over R that a specific x, there is a mistake. Okay, there is a mistake. Mistake for x. Okay. And this is at most 2 to the minus n. It is strictly less than 2 to the minus n. So this is strictly less than 1. Okay. So the probability that no R works for all x is less than 1. It means that there is an x, there is an R, sorry, that works for every x. Okay. So I'm not sure it was very clear, but you just used the union bound and you have reduced your probability of error so much that actually you have this probability here that this is the probability over R that actually it fails on some x. This is less than 1. It means that there is at least one R that works for all x, yes. Yes. This is, oh yeah, this is using the algorithm with this error. So we take our first algorithm, we reduce the error, and we do this argument. Yeah. Oh yeah. Okay. So why do we care about that? We care because it's related to circuits, actually. So let me explain very briefly what it is. Now it means that if you are given such an R, actually you can decide in deterministic time, polynomial time, your algorithm, your problem, sorry. So it means that if you are given Rn, then you can decide in deterministic polynomial time your problem. So instead of randomizing, you just give the right advice here, the right word, Rn, that works for all inputs. Okay. So this will be called an advice. And it works, this is one advice for all, so one advice for all words x of size n. Okay? And this new class, actually, where you can decide something in deterministic polynomial time with an advice of polynomial size for each length, this is called the class p/poly. So think of p with an advice of polynomial size. Okay? So this is something that helps your machine, but this must be the same for all words of same length. Okay? And actually, I will not comment further on that, but this is the same as circuits, Boolean circuits. Circuits of polynomial size. So we'll not explain further, but this is the same class. And why do I speak about that? Because we have actually, what we have proven here is that BBP or CoRP, let's say, is the same, is in p/poly. This is what we have proven here. Okay. So it has Boolean circuits of polynomial size. And actually, if we compare to other classes, we suppose that P is equal to CoRP. So this is an open question, but a central one. So we suppose that we can de-randomize every problem here. We can remove the randomness. That is kind of what we've done with this proposition here, that if we are given an advice, we can remove randomness. Okay? This is what we want to do here, but we want to construct Rn, which is not easy. Okay? So this is still open, and we don't know, for instance, how to separate CoRP from exp. So most people think that this is true. That would imply this, due to the time hierarchy theorem that we've seen one day. But we don't know how to separate these two classes. This is a huge class. This is a class of efficient problems, let's say, but we don't know how to separate them. And this is related. So why do people think that this is true? Because if we have lower bounds on circuits, so meaning that we have problems that we can show hard, then we obtain this de-randomization. So let me sketch this. Remember PIT. PIT, a natural strategy to de-randomize PIT. What it is, so de-randomize means find an equivalent deterministic polynomial time algorithm. Okay? So we want to remove randomness. So de-randomized PIT is construct M1, M, let's say K, random numbers, as before, and then accept if and only if n is 0 modulo mi for all I. Okay? So this will be a natural way to de-randomize. We mimic the strategy of the randomized algorithm, but we construct the modulo instead of taking them at random. Okay? But if we have if this works, so if this algorithm is okay, so what will we have if this is okay? If we manage to construct such points m sub I, if we manage to construct such points n sub I, what will happen? It will happen that we will have actually a lower bound. So let's try to understand why. And this is the link I wanted to do between lower bounds and de-randomization. So let me explain that. Okay, so proposition, let's say. So if for arithmetic circuits of size m, so this is the input of PIT, okay? We can construct M1, MK, such that so this is C, okay. C is 0 if and only if for I, C is 0 modulo Mi. Okay, so this is the natural de-randomization that we could hope for. So you have an arithmetic circuit C, and you wonder whether it is 0, and you just have to evaluate modulo Mi for the Mi that you have constructed. Okay, so these are natural things to do. So what happens then? Then the integer, okay, the integer product of the Mi fools this test. It means that it is different from 0, but it is accepted by this test. It fools this algorithm, okay? Fools this algorithm. Hence, it means that actually this number here does not have arithmetic circuits of size n. It cannot have arithmetic circuits of size n because our algorithm works for all circuits of size n, and it is fooled by this. So it cannot have, let me call it, I don't know, n sub 0, okay. N0 does not have arithmetic circuits of size n. And you have a lower bound. You have shown that this particular integer does not have arithmetic circuits of size n. Okay? So this is a link between de-randomization and lower bound. This is a lower bound on circuits, and you show that this particular integer does not have arithmetic circuits of size n. Actually, we can do more. It can be generalized, and we can show something like PIT. If we can de-randomize PIT in any possible way, here we have supposed that we de-randomize it in a very particular way. But if we can de-randomize PIT in any possible way, okay, then we will have a lower bound on next, which is a huge class, non-deterministic exponential time. Okay, so a lower bound on the circuit size for next, or on the permanent, so I won't say what it is, or the permanent does not have arithmetic circuits of Police size. Okay, so this is kind of a strange lower bound here, but this is the best we can do so far. If you can de-randomize, then you have a kind of lower bound on circuits. So this is not an easy result, actually. This is Impagliazzo and Cabanets who've shown that. And actually, we have also the converse. If we have very strong lower bounds, so let me try to write that, but this is very, I mean, this is a very complicated result. But if we have lower bounds, then we can de-randomize. So we have kind of an equivalence between de-randomization and lower bounds, circuit lower bounds. So the other direction, so this is a long line of work, starting with Yao and then Nissan and Wigderson, and then Impagliazzo, Cabadens also, and many others. And they show that if you have, for instance, exp not in P/poly, so that means that this class exp, exponential deterministic time, which is a large class, does not have circuits of polymorph size, as we've seen, okay? Then, actually, we can de-randomize a little bit BPP. So BPP is in, okay, let me write it. The little, I mean, a little better than exponential. Okay. So you are in 2 to the n to the epsilon for any epsilon. Okay, so you can do a little better than the naive way to just test all possible random words. Okay. Okay, and if you have a better lower bound here, you can go up to de-randomizing completely BPP, meaning that you can have BPP equals P. That is why, I mean, people believe in lower bounds, so that is why people believe in de-randomization, actually, roughly speaking. All right, questions? Okay, so I think, sorry, yeah, please, before I just introduce something, yeah.
Could you draw a big picture of with potatoes at some point?
Yes, I will do that, okay. Thank you, Pierre. Yes, I can. So what do we have? We have the class, among the classes we have seen, we have P, which is the most efficient, let's say, algorithms that we've seen so far, deterministic polymorph time. Then we have, let's say, RP, which probably is equal to P, but we don't know yet, okay? And which is included in NP. Okay. And probably NP is different from P. So probably these two classes are equal, but these two are different, okay? Then we have the class, so let me draw, okay, yes, I should have made them blue for for randomized, let's say. And you have the class BPP, which probably is equal to P, but we don't know if it is included in NP, okay? But anyway. So, okay, not sure, something like this. And then we have, so among the classes that we've seen, we have, okay, a very particular class B/poly, which contains BPP, which probably does not contain NP, but which is not countable. So that's why I'm just drawing it like this. This is an uncountable class, contrary to the other ones that are countable. Okay, because the advice sequence here is uncountable, so we can have many more languages, but probably NP is not contained in P/poly, we don't really know. And then we have the class, okay, let me in white, we have the class exp here, which contains BPP, NP, and so on, because you can all simulate by enumerating the random bits and so on. And which probably is not contained in P/poly either, of course. And then next is above that, and we don't even know, okay, we don't know if X is different from RP. We know it is different from P. We know it is different from P because of the time hierarchy theorem, okay? And if you have NEXP, if I draw another class here, NEXP, so this is NEXP, we don't know if it is different from BPP. It might be that NEXP is equal to BPP, okay? Oh, it might not be, but probably not. But we don't know how to rule out this possibility that NEXP is equal to BPP. And still, it is but it is different from NP. NEXP is different from NP because you have the similar time hierarchy theorem for non-deterministic time. Okay. Is that clear? Yeah. Okay. And then in the 10 remaining minutes, let me just briefly mention Kolmogorov complexity, because maybe you will hear, for sure you will hear about that in the 4th week, for if you go there. So, and I will try to make a link with what we've seen right now. So, suppose suppose you want to define what is a random sequence. If you use probability theory, it doesn't help much, because the probability of the sequence 0, 0, 0, 0 n times is equal to any other probability of any other random sequence if you just take if you just throw a coin at random. Okay, so this is equal to 0, 0, 1, 1, 1. I mean the same probability, where you seem to have a much more random sequence. Okay, so probability does not help in defining randomness in some sense. This is a bit strange, but it is the way it is. Okay, and so what tools do we have to define randomness? One of the tools is to use Kolmogorov complexity. So I will just sketch the ideas, because I do not have much time left. And then we'll try to understand the links with de-randomization right before. Okay, so definition, what is the Kolmogorov complexity of a sequence? You will see that a Kolmogorov complexity of the first sequence is very small, okay? And the Kolmogorov complexity of a random sequence, true what we have in mind by random, will be high. So that's the way we can define randomness, actually. So, okay. Okay, so how do we define Kolmogorov complexity? First, you have to take a universal machine, a universal Turing machine, meaning a universal language, programming language, like, for instance, Python or Java or whatever. So take a universal machine, Turing machine, U, okay? This will be the interpreter, let's say, and we can execute, U can execute a code that you give to it. So universal means that it can execute a program given to it. An arbitrary program. An arbitrary program that you give it. So, for instance, let's say a program P, in the sense that U of Px executes the program P on input X. Okay? So this is just an interpreter. You give it P, you give it an input, and you execute P on X. Okay? So this is what we call a universal Turing machine. And you define a complexity according to this machine. C, so Cu. It depends on the machine you choose, actually. Cu of X is the length of the smallest program that prints X. So imagine the Kolmogorov complexity. If you use U, if U is Python, for instance, then this will be the size of the smallest Python program that is able to print X. Okay? So example. So if U is Python, then Cu of X is always less than size of X plus some constant. So what is the constant? This is the length of the instruction print, okay? Because you have always the program print of x, which is of length a constant plus the size of x. So this program always achieves the correct thing, meaning that the complexity of a string x is always bounded by the size of x plus a constant. Okay? So you will tell me that, okay, this is because we have chosen a correct machine u. Indeed, it depends on u. But actually, what you can do is to choose the best possible u in some sense. Okay? So there is, let's say, best possible u in the sense that for all other machine m, cu of x is always less than a constant depending on m plus cm. Okay, this is not a good constant name, plus cm of u. So you can choose a universal machine u that is kind of better up to a constant than every other machine m. Okay, and this will be the machine that we will choose. So you're going to have several machines, but they are all equivalent to up to a constant. Okay, so this is the definition of the Kolmogorov complexity. Is that roughly clear? So this is how much you can compress a string x by a machine u in some sense. Okay, the smallest program that can print x is the best possible compression of x. And intuitively, you see that the let's say the more random the sequence, the less compressible it is. You cannot predict the bits, so it is incompressible. This is exactly what we will call Kolmogorov random. So Kolmogorov randomness will be when it is not compressible. Okay. So let me, okay, definition. X is, okay, let's say C Kolmogorov random if the complexity, so now I drop the subscript u because we have chosen a fixed machine, one of the best machines possible. C of x is at least the size of x minus the constant c. Okay? In that case, we say it is C Kolmogorov random. And actually, if we, and actually there are some such strings. So how can you see that there are such strings? So the number of x such that the complexity of x is bounded by, let's say, t, right, is at most 2 to the t plus 1. So why? Because the number of programs here that are of size at most t is the number of programs of size 0 plus the number of programs of size 1 plus the number of programs of size 2 and so on. So this is a sum of the 2 to the I up to t. So it is 2 to the t plus 1 minus 1, but anyway, it doesn't matter. So you have such a number of words of small complexity. Okay? And now it means that since the total number of x is 2 to the n, it means that there are, okay, there are words that are, let's say, one Kolmogorov random, one random, for instance, okay, or even 0 random actually. Okay. Is that clear? So there are words that are random. And now in the remaining minute, let me try to explain how it relates to de-randomization by using these random words. Here, how can we do? If you take, okay, if you have the word Rn, sorry, before, that worked for all input lengths x, if R sub n, okay, if you have a language A in, let's say, BPP, such that the okay, and as before, words are n such that the probability, okay, such that x is in A, if and only if you know you have this particular derandomizing string Rn, which is in B, as before. Okay, so Rn is of polynomial size. This is a choice of random bits that work for all x, all possible x, for all x. Okay, you remember that? So this is the way. Then what I'm claiming that actually the Kolmogorov complexity of Rn is not sorry, I need not make a mistake again. What I mean is that, okay, I will make a mistake again. So sorry, let me let me think a little bit. What I mean, okay, what I want to say is that, and probably I will leave it as an exercise, otherwise I will just don't have time. So exercise. Exercise. So if R is, let's say, okay, one random, then it can be used to de-randomize a problem in BPP, for instance. So what do I mean by that? You just replace the random bits by R, okay? And if you have dropped the error rate sufficiently, then R will work for all words X, and so it will de-randomize the problem in BPP, okay? So you can try to do that, and yeah, this is an interesting exercise, but I will just leave it for the moment, otherwise I will make a mistake. So thank you, and yeah.
So we have time for a few quick questions. Does anyone have questions?
So perhaps you mentioned it, but is the converse hold that R must be one random or close to it? I mean, the complexity of R must be very high no matter what, I would guess. So
the converse of this? No, hopefully not. We don't know any such thing. Okay, let me think a little bit, if I'm not mistaken. No, we don't know any such thing because the goal of de-randomization is probably to build, actually to construct such an R that works for any X. And if we want to construct it, it will have small complexity, okay? Yeah.
That's sort of the flip side of the question, is that these are, you can construct these then, you say? That there are techniques for coming up with these de-randomizers?
No, we don't know any technique like this. Yeah, it is the whole point actually. What I mentioned before is that if we can do that, we can prove lower bounds or whatever, but actually we don't know how to construct a string that de-randomizes RP or BPP, and we don't know how to do that. So people have managed to do that for some particular problems, and probably the next problem that is looked in the field is PIT that I mentioned, and but this seems to be very hard. So we have some partial results, like for instance PIT on arithmetic circuits of constant depth or something like that. We can randomize. So, but this is not the same technique as that. We do not construct directly such a thing. Okay, we have different ways to do that. But this technique, we don't know at all how to do. Yeah.
Any more questions?
maybe one point that is worth to mention is that, I mean, it's actually the Kolmogorov complexity is uncomputable.
Yes.
So constructing this, I mean, it's a bit. I mean,
No, of course. Okay, I'm not sure. I'm not sure the question was to construct a random one random string. Okay, this is indeed impossible to do it constructively, but probably to construct a string that was enough to de-randomize BPP. I hope. I mean, that's what I understood. But yeah, thank you. Indeed, Kolmogorov complexity is uncomputable. Okay, you cannot compute the complexity of one. I mean, maybe I can just elaborate on that because it might be interesting. So C of, the function C is uncomputable. So you cannot compute it, uncomputable. So why otherwise? Otherwise, you would have a program of some size, let's say K, for C, okay? And then you could build a paradox, let's say, and you can write the following program. Okay, so you start with n is 0. You will enumerate all the n's until you find an n of sufficiently large Kolmogorov complexity. Donc, while the Kolmogorov complexity C of n, okay, this is an integer or a word. I mean, this is the same. While it is less than k plus, let's say, 1000 anyway, it doesn't matter. What do? You just increment n, okay? You go to the next n, and then at the end, you print n. So if C of n had a program of size k, this whole program has a size less than k plus 1000, okay? But it outputs an n which is of complexity more than k plus 1000. Okay, and this is a paradox. So it shows that you cannot have a program of size k for this function C. Yeah, you cannot have a program size k, and the reasoning is valid for all k. So you cannot have a program for C, indeed. So it is uncomputable. Yeah. Thank you for the remark.
Maybe a last very quick question.
Can you give some brief references for these results about BPP versus the deep theorem that you mentioned,
yes,
which relates all of these many things?
Of course, I should have mentioned it earlier. So, probably two books that are reference books. You have this book by Aurora and Barak. Maybe there is a C here. Probably, I don't know. Anyway, which dates back from maybe 2010, I don't know, or yeah, maybe 2009, I don't know, something like this, which is modern computational complexity or something like this. Modern, I'm not sure, but okay. So it explains. In a high-level view, let's say, modern approach. Yeah, computer. Thank you. A modern approach. Modern approach. So it's a very interesting book that describes a lot more than what I explained, and in particular the links between de-randomization and lower bound. And if you want to go deeper into Kolmogorov complexity, which is very interesting, you have the book by Lee and Vitani. Not sure about how you write. Okay. And which is probably titled like Kolmogorov complexity, something like this. and which is older than this one, but I don't know the year, so Kolmogorov complexity.
I guess Kolmogorov complexity and its application.
Thank you. Kolmogorov complexity and its applications. Yes, thank you for the titles. And there are two very good books that you can read without damage. Okay.
So we can thank Sylvain once more.